Have you ever found yourself pausing to truly wonder why absolutely everything within this vast universe is in a constant state of spinning? And yet, right here and right now, we feel completely and utterly still. Consider this. The Earth is currently turning beneath us at a speed of over 1,000 miles per hour. It is orbiting the Sun at a distance of 93 million miles away, while the entire solar system itself races through the galaxy at nearly 500,000 miles per hour. And still, despite all this velocity, we do not feel a single thing. Our heartbeat does not tremble in response. Our breath does not sway or shake as if we were frozen inside a universe that is constantly in motion. But what if that sensation of stillness is actually the greatest illusion of all? What if time itself is just the echoing resonance of a much deeper rotation? A rotation that began before the existence of atoms, before the first light shone, and before memory itself. Tonight, we are going to drift deep into that mystery. We are going to ask not just why things move, but why nothing in existence can ever stop moving. So, please, close your eyes. Let the sound of the cosmos hum beneath your skin, and follow me into the spinning heart of everything. Before we begin this journey, if you are kind enough to do so, a gentle like or a quiet tap on the subscribe button would mean the world to me. It is a small gesture on your part, but I hold it with deep gratitude, because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories still find their way to gentle hearts just like yours. Now, let us begin with the first question. Part 1. If everything in the universe is spinning, why do we feel frozen in time? The Earth is turning at a speed of over 1,000 miles per hour, spinning steadily beneath your feet at this very moment. At the same time, it rushes around the Sun at a speed of nearly 67,000 miles per hour. And even as you breathe right now, the entire solar system sails around the Milky Way galaxy at a speed of almost 490,000 miles per hour. Yet somehow, against all logic, we do not feel any of it. The coffee in your cup does not ripple. The air does not drag against your skin. The stars above appear perfectly still. It is one of the great illusions of existence, a paradox of motion and calm. From the smallest electron to the largest cluster of galaxies, everything in the universe spins. Atoms rotate. Planets revolve. Galaxies twist in vast spirals composed of light and dust. Even the universe itself, according to some cosmological models, may have a subtle global rotation written into its very fabric. But why, if everything is constantly in motion, do we feel so incredibly still? The answer begins with inertia, one of the most quiet yet powerful principles in the field of physics. Isaac Newton first described it in the 17th century. An object in motion stays in motion unless acted upon by an external force. This law is the secret reason we do not feel the Earth's endless spinning. We are moving with the Earth, not against it. Your body, the air around you, the ocean, the mountains, all of it turns together, locked in a single, silent rhythm. To feel motion, you need a difference. You need a push, a pull, or a change in speed. But there is no such change here. The Earth's spin is constant, smooth, and ancient. It is the same now as it was when early humans first looked up at the stars. Astronauts, too, experience this illusion on a grander scale. In orbit, they travel at 17,500 miles per hour, circling the planet every 90 minutes. Yet, inside the spacecraft, everything feels calm. Without resistance, without air friction, motion feels exactly like stillness. This phenomenon has a name: uniform motion. It is the same principle that allows you to comfortably sip tea on an airplane traveling at 500 miles per hour. You and the plane move together. Only when turbulence, a sudden change, interrupts that uniformity, do you actually feel the movement. The Earth's motion, too, is seamless. There is no vibration, no friction, and no sudden shifts. And because space is almost a perfect vacuum, there is nothing out there to remind us that we are spinning at cosmic speeds. Neil deGrasse Tyson once said, "We are on a space rock that is orbiting a star that is orbiting a galaxy that is moving through the universe, and we call it home." It is easy to forget this because our senses were never built for such massive scales. Our inner ears, which detect motion and balance, evolved to handle walking, running, or climbing, not the rotation of a planet thousands of miles wide. They respond to acceleration, not to steady velocity. That is why you feel the start of a car, but not its cruising speed. On Earth, everything moves with you. There is no start or stop, only an eternal glide. Yet, scientists can measure this hidden motion with remarkable precision. The Foucault pendulum, first demonstrated in the year 1851 by Léon Foucault, swings freely back and forth while the ground beneath it slowly turns. It does not need the stars to prove Earth's rotation. Its slow twist over the hours is the Earth's spin visualized in silence. If you have ever stood near one of these pendulums in a museum, you have seen time and motion merge, one gentle swing at a time. On a cosmic scale, this rotation is far from trivial. The Earth's spin defines day and night, stabilizes the planet's magnetic field, and protects us from solar radiation. Without it, our world would be scorched on one side and frozen on the other. NASA's Goddard Space Flight Center notes that the planet's rotation has been slowing slightly over billions of years, mostly due to the Moon's tidal pull adding about 1.7 milliseconds to the length, and of each century's day. So even in our stillness, there is change, slow, invisible, but real. When we look deeper, rotation is not just an earthly phenomenon. It is a cosmic signature. Stars form from collapsing clouds of gas and dust, and as they shrink, they spin faster. This is a conservation of angular momentum, the very same law that makes a figure skater spin faster when pulling in her arms. Every planet inherits this momentum. The Earth's 24-hour rotation is a fossilized trace of that ancient whirlpool of creation. Even the Sun spins once every 27 days, dragging its magnetic field through space like glowing threads. And the Milky Way, our galactic home, turns once every 230 million years, carrying hundreds of billions of stars in a spiral dance that began long before our planet existed. The James Webb Space Telescope has captured galaxies so far away that their light has been traveling for over 13 billion years. And even those primordial galaxies show signs of rotation. Scientists studying these early formations found subtle differences in light. One side was slightly red-shifted, the other blue-shifted, a telltale signature of spin. It seems that the tendency to rotate is written into the DNA of the universe. But how can everything be spinning and yet feel so still? Part of the answer lies in relativity. According to Einstein, there is no absolute motion, only motion relative to something else. So, from our perspective on Earth, we are at rest, and it is the universe that moves. From another frame of reference, the opposite is true. This symmetry is what keeps physics consistent, and what makes our stillness an illusion of perspective. In deep space, astronauts aboard the International Space Station orbit Earth at nearly 5 miles per second. But they experience weightlessness, not motion. Their sense of down changes every 90 minutes, yet their minds adapt. We too are passengers in motion, adapted to calm. Our stillness is a form of survival, a balance between what our senses can bear and what the cosmos demands. If we could somehow feel the motion of the Earth, the pull of the Sun, and the drift of the galaxy, our perception of time itself would unravel, because motion and time are intertwined. As rotation defines days and years, it also defines the heartbeat of the cosmos. Time, as Carl Sagan once said, is woven into the very fabric of the universe. And we are the thread. The quiet you feel now is not the absence of motion. It is the harmony of everything moving together. So when you lie down tonight beneath the invisible turning of the stars, remember this: you are not standing still. You are gliding through a cosmic river, gently, constantly, endlessly. Each moment of stillness is just the universe moving too smoothly for you to notice. And in that perfect balance of motion and calm, life finds its quiet rhythm. Take a slow breath. You are spinning, always have been. And the silence you hear is the sound of everything moving together. Now, as we drift deeper into this story, let us look backward to the moment before motion began. When the universe itself took its first turn, that is where our next chapter begins. Part 2. Who set the universe spinning? If you could turn back time, not centuries, not millennia, but all the way to the first second after the Big Bang, what would you see? Would there be light? Would there be sound? Or would there only be a sudden motion, a swirl, a twist, the very first rotation of everything that would ever exist? The question of who or what gave the universe its first spin is not a question of philosophy, but of physics. It lies buried deep within the equations of cosmology, inside the earliest moments of time when matter, energy, and space itself began to unfold. Astronomers call this the Planck era, a window so early, within 10 to the power of negative 43 seconds of the Big Bang, that our current laws of physics cannot fully describe it. But what little we can infer suggests something extraordinary. The universe may have been born not in silence, but in a gentle rotation. Today, scientists studying the cosmic microwave background, the faint afterglow of the Big Bang detected by satellites like WMAP and Planck, have found tiny irregularities. These are small ripples in temperature, only a few millionths of a degree apart. These patterns tell us that the early universe was not perfectly uniform. There were slight differences, and those differences grew into everything we see today: galaxies, stars, planets, and life itself. But some researchers noticed something stranger: a faint alignment, a kind of large-scale twist in the distribution of those ripples. They called it the axis of evil, a mysterious pattern suggesting that the universe on the largest scales might have a preferred direction of rotation. According to data from NASA's WMAP mission and follow-up observations by the Planck satellite, this alignment could mean one of two things: either a subtle artifact of measurement or evidence that the entire universe once spun. If true, that spin might have shaped everything from the spiral arms of galaxies to the very arrow of time. How could such a rotation begin? The key might lie in quantum fluctuations, tiny, random changes in energy that occurred when the universe was smaller than an atom. Even in complete emptiness, these fluctuations happen naturally. As NASA's Goddard Space Flight Center describes, quantum fields are never perfectly still. They jitter. When the Big Bang happened, those jitters were stretched and amplified by cosmic inflation, a brief but explosive expansion that made the universe grow faster than the speed of light. That rapid stretching could have turned some of those quantum jitters into swirling motions, the first cosmic spins. Inflation theory, proposed by physicist Alan Guth in the year 1981, explains why the universe appears so smooth and uniform, yet still contains the seeds of structure. But in recent years, data from Planck and BICEP-2 experiments suggested that during inflation, subtle rotational modes known as B-modes may have existed in the primordial gravitational waves. These tiny curls in spacetime could be the fossil record of the universe's first rotation. They show that the Big Bang was not just an explosion, but a twisting birth, one that imprinted spin across every scale of matter. And this makes sense when we look at what happened next. As the universe expanded and cooled, matter began to form. First quarks and gluons, then protons and neutrons, then atoms. Each carried tiny amounts of angular momentum. When gravity later gathered them into clouds and galaxies, That ancient angular momentum was conserved. It is the same principle that makes a figure skater spin faster by pulling in her arms. In physics, nothing spins from nothing. Motion must come from motion. And so the first spin, however small, had to exist from the beginning. Astronomers today can see the fingerprints of that rotation in distant galaxies. In the year 2011, researchers from the Harvard-Smithsonian Center for Astrophysics analyzed over 15,000 spiral galaxies and found a subtle preference in their rotation direction, an imbalance that might trace back to the early universe's spin. While not yet conclusive, this handedness of the cosmos hints that our universe may not be entirely random after all. There may be a hidden rhythm, a silent turn that everything still follows. Even dark matter, that invisible scaffolding that holds galaxies together, could carry a spin signature. Computer simulations by NASA's Jet Propulsion Laboratory show that dark matter halos twist and rotate over billions of years, guiding the visible galaxies within them like whirlpools guiding leaves. Without that rotation, galaxies would tear themselves apart. It is as if the early universe set everything spinning. And even now, the echoes of that motion keep the stars in balance. Still, the origin question remains. Who or what began the spin? Physicists lean on one quiet answer: symmetry breaking. In the earliest fractions of a second, forces we now know as gravity, electromagnetism, and the nuclear forces were once united. But as the universe cooled, they began to split apart. When that symmetry broke, tiny asymmetries, tiny imperfections appeared. Those imperfections, according to the European Space Agency, are what allowed structure, motion, and spin to exist. In a perfectly balanced universe, nothing could move. But in a slightly unbalanced one, it could dance. We can see this principle mirrored everywhere. In the direction galaxies spin, in the way atoms rotate, even in the way neutrinos have a left-handed preference. Nature, it seems, is not perfectly symmetrical, and that tiny flaw is what allows everything to turn. Some scientists have even tried to detect whether the entire universe is rotating. In the year 2020, astrophysicist Lior Shamir from Kansas State University analyzed over 200,000 galaxies from the Sloan Digital Sky Survey. He found that galaxies in one half of the sky tend to rotate more in one direction than the other, suggesting a large-scale cosmic spin. As Shamir wrote, the universe may have a collective pattern of motion, a preferred direction that began in the early universe. This does not mean the cosmos is spinning like a top. Rather, it might mean that the fabric of spacetime itself once twisted slightly during its expansion. Even a subtle twist could cascade across billions of light years. To us, it feels invisible, but on a universal scale, it could shape the geometry of everything. To test these theories, NASA and the European Space Agency continue to map the universe in increasing detail. The James Webb Space Telescope is already capturing the light of galaxies that formed just 300 million years after the Big Bang. Some of these ancient systems already show organized rotation spiral patterns far too early in cosmic history to be explained by chance. That means the seeds of spin were planted almost immediately. The universe did not have to learn to rotate. It was born turning. Even on the quantum level, spin is fundamental. Every particle, electrons, protons, neutrons, carries intrinsic spin, a built-in property of matter described by quantum mechanics. It is not the kind of spinning we imagine physically, but a deeper mathematical rotation encoded in the wave function itself. As physicist Richard Feynman once said, spin is one of the most profound properties of nature. It is not that the particle is literally spinning. It simply has spin as it has mass. So, in a way, rotation was not added later. It was part of the blueprint of existence. When you look at the night sky, you are seeing the inheritance of that motion. Every galaxy's swirl, every planet's orbit, every photon of light, all descend from that first cosmic rotation. Without it, matter would never have clumped, stars would never have formed, and time itself would have no rhythm. Motion is not an accident of the universe. It is its heartbeat. And though we may never know exactly what triggered that first spin, the evidence keeps whispering that it has always been there, quiet, steady, invisible, yet written into everything we can see. As cosmologist Jan Tauber once said, "The universe carries memory not in words but in patterns of light, and within those patterns lies the faint signature of the first motion, a twist older than time itself." So when we ask who set the universe spinning, the most honest answer may be that the universe never learned to move. It was born already in motion. The spin wasn't created. It was inherited. Take a breath. The atoms in your body, too, are still turning with that first impulse. From the tiniest electron to the swirl of the Milky Way, the same rotation continues, unbroken for nearly 13.8 billion years. We are not separate from that motion. We are its continuation. And as we move onward through this story, we arrive at the next question, one that flows naturally from the last. If rotation shaped the birth of the universe, could it also be the reason life itself exists? That is where we turn next. Part 3. Did spinning make life possible? Without rotation, Earth would be silent. No day, no night, no weather, only a frozen side and a scorched one, a dead world, adrift in light. But because it spins, this planet breathes. Every sunrise, every wave, every gust of wind, they all come from the same ancient turn that began 4.5 billion years ago. The Earth's spin is not just a motion, it is an engine, a delicate balance that sustains everything we know as life. From the magnetic field that shields us from cosmic radiation to the cycles of temperature that nurture oceans and clouds, rotation shapes our world in ways both visible and invisible. According to NASA's Goddard Space Flight Center, our planet's rotation speed near the equator is about 1,037 miles per hour, completing one full spin every 23 hours, 56 minutes, and 4 seconds, what scientists call a sidereal day. This steady rhythm sets the pace for all biological and environmental cycles on Earth. Every plant, animal, and ocean current is synchronized to it, an invisible metronome ticking beneath everything alive. The first consequence of Earth's rotation is the alternation of day and night. It distributes sunlight across the surface, creating temperature gradients that drive wind, currents, and weather. Without that daily rotation, one hemisphere would roast under perpetual daylight, while the other froze in eternal darkness. The boundary between them would be a violent wall of storms, a lifeless twilight zone. But because Earth spins, the sun rises and sets, and energy is shared evenly enough to allow stable climates and habitable regions. Rotation also affects Earth's magnetic field, one of the most crucial shields for life. Deep beneath our feet, the planet's liquid iron core moves and churns, generating a magnetic dynamo. As NASA's magnetospheric multiscale mission describes it, the Earth's magnetic field is created by the motion of molten iron within its core. This field deflects the solar wind, a stream of charged particles constantly emitted by the sun. Without it, those particles would strip away our atmosphere, much like what happened on Mars. The red planet spins once every 24.6 hours, almost like Earth. But its smaller, cooled core lost its molten motion long ago. Without a working magnetic field, its air was slowly eroded by the sun's radiation, leaving behind a dry, frozen desert. Here on Earth, the magnetic field also shapes the auroras, those soft glowing curtains of light near the poles. They are not just beauty, they are proof of protection. Where magnetic lines bend and interact with charged solar particles, light is born, a reminder that our planet's rotation still powers an invisible force field around us. But the spin's influence does not stop at shielding and sunlight. It also governs the atmosphere itself. Because Earth turns, air moving from the equator toward the poles curves, a phenomenon known as the Coriolis effect. This effect creates the vast spiraling systems of winds and currents that define our weather. It is why hurricanes spin, why jet streams flow, and why ocean gyres carry warm and cold water across the globe. Without the Coriolis effect, weather patterns would collapse into chaos, storms would not form, and climates would not balance. In fact, the rotation speed of a planet directly shapes its climate. NASA's Global Modeling and Assimilation Office has simulated exoplanets with slower or faster spins. A slower rotation causes one side to overheat and the other to freeze, while a faster one can generate extreme winds and shorter days that disrupt atmospheric stability. Earth's 24-hour rhythm is almost perfect, long enough to distribute energy evenly, but short enough to prevent overheating. The length of day also affects biology. Living organisms evolved internal clocks, circadian rhythms that align with the planet's rotation. According to research published by the National Center for Biotechnology Information, every living cell on Earth carries a molecular timekeeper that syncs to this 24-hour cycle. This rhythm regulates when plants open their leaves, when birds migrate, and even when humans sleep. If the Earth stopped rotating, this biological harmony would shatter. Light and dark would no longer alternate regularly, and life as we know it could not adapt. Rotation also shaped how the Moon became our companion. Billions of years ago, a Mars-sized object named Theia collided with the young Earth. The impact sent debris into orbit, which later coalesced into the Moon. The collision also increased Earth's spin dramatically. Over time, the Moon's gravity has been slowing that spin, gradually lengthening our days from about 6 hours to the 24-hour cycle we have now. Tidal forces between the two bodies keep the planet's axial tilt stable, preventing extreme climate swings. The Gaia mission confirms that this stability is essential for long-term habitability. Planets that wobble too much often experience catastrophic climate variations. The Moon and Earth now exist in a slow, gravitational embrace. The same tides that shape our oceans also slow our rotation by about 1.7 milliseconds per century, as recorded by NASA's Jet Propulsion Laboratory. It is a reminder that even the length of our day, the heartbeat of our world, is gradually changing. One imperceptible moment at a time. If we look beyond our planet, we find that rotation plays a similar role in other worlds. Jupiter, for example, spins once every 9 hours and 56 minutes, making it the fastest rotating planet in the solar system. Its speed drives ferocious jet streams and storms, including the Great Red Spot, a hurricane larger than Earth that has raged for centuries. Rotation there creates chaos yet also stability, distributing heat and shaping the planet's banded beauty. Meanwhile, Venus, which rotates backward and extremely slowly, one full rotation every 243 Earth days, has almost no magnetic field. Its thick carbon dioxide atmosphere traps heat in a runaway greenhouse effect, making it the hottest planet in the solar system. The comparison is striking. Too fast and storms dominate. Too slow and protection disappears. Even Mars, with a day just 40 minutes longer than ours, shows what happens when internal motion fades. As its core cooled, its once strong magnetic field vanished, allowing solar radiation to strip away its air and water. The faint remnants of magnetism still linger in the crust, ghostly traces of a spin that once sustained a dynamic world. Rotation, then, is not optional for habitability. It is fundamental. In the year 2023, scientists using the James Webb Space Telescope observed exoplanets like WASP-39b and TRAPPIST-1e, discovering that those with measurable spin or atmospheric circulation show clearer signs of chemical balance and temperature distribution. Without rotation, energy remains trapped or lost, creating unstable environments. As NASA's Exoplanet Exploration Program summarizes, rotation plays a critical role in determining the climate and potential habitability of a planet. Rotation may also be tied to magnetic protection on distant worlds. A 2021 study by the Harvard-Smithsonian Center for Astrophysics noted that exoplanets with rapid spins tend to maintain molten metallic cores longer, extending the life of their magnetic fields. Those fields in turn shield atmospheres and may increase the likelihood of surface liquid water, the essential ingredient of life. So when we ask, did spinning make life possible? The data says yes. Rotation shapes everything from a planet's day length to its temperature gradients, atmosphere, weather, and magnetic safety. Life, it seems, thrives not despite motion, but because of it. Our world's rotation speed has changed over eons, yet its effects continue to echo across time. It controls the rhythm of tides, the growth of forests, the migrations of animals. It defines our sense of time itself, not as an abstract idea, but as the physical turning of the world beneath us. As astrophysicist Neil deGrasse Tyson once said, "We are not just in the universe, we are of the universe. The Earth turns, and so do we." Take a moment to simply listen to that turn. Every rotation carries the whisper of 4.5 billion years of balance and motion. If Earth stopped spinning tomorrow, the oceans would surge toward the poles, the atmosphere would collapse into chaos, and the planet would lose its breath. But tonight, as it spins gently beneath you, everything still works perfectly, quietly, continuously. So perhaps it is no exaggeration to say that the rotation of Earth is the quiet architect of life. The same cosmic motion that once swirled dust into a planet now spins that planet into morning, into wind, into rain, into you. Now, as we drift deeper into this journey, let us follow that rotation outward to where spinning no longer shapes life, but begins to bend something even stranger. Because beyond a certain speed, rotation does not just move matter, it can start to twist time itself. And that is where our next chapter begins. Part 4. Can rotation bend time itself? When rotation reaches its limit, it stops being motion and becomes distortion. At extreme speeds, turning objects no longer just move through space. They begin to pull at time itself. Einstein's general theory of relativity, published in the year 1915, predicted that gravity and motion are inseparable, two expressions of how mass curves spacetime. The greater the energy or spin of an object, the more it twists the geometry around it. This twisting of spacetime by rotation is called frame dragging, and it is one of the most subtle, beautiful, and verified predictions of modern physics. Imagine spacetime as a calm lake. When a massive object spins, like the Earth or a black hole, it stirs that lake, creating tiny vortices in the very flow of time. In those whirlpools, the direction of time itself can begin to curve. NASA physicist Francis Everett, who led the gravity probe B experiment, once described it like this: "As the Earth rotates, it drags spacetime around with it, much like a spinning sphere twisting the honey in which it is immersed." Gravity probe B, launched in the year 2004, used 4 ultra-precise gyroscopes orbiting 400 miles above Earth to measure this effect. After a year of observation, NASA confirmed that our planet's rotation drags spacetime by about 0.000011 degrees per year. That may sound small, but it matches Einstein's equations with extraordinary precision. Even our gentle planet, spinning once every 24 hours, is capable of bending the flow of time. Now, imagine a rotation billions of times faster and a gravitational field billions of times stronger. That is what happens near a neutron star. When a massive star dies, it collapses under its own gravity, squeezing matter so tightly that protons and electrons merge into neutrons. The result is an object only about 12 miles wide, but with a mass greater than that of our Sun. To conserve angular momentum, these stars spin unimaginably fast, up to 700 times per second. Astronomers call them pulsars because their magnetic poles emit beams of radiation that sweep across space like cosmic lighthouses. As they rotate, they create the strongest known magnetic fields in the universe and twist spacetime so violently that even light struggles to travel in straight lines. NASA's NICER instrument aboard the International Space Station has mapped these distortions, showing that time near a pulsar ticks more slowly than it does on Earth. The stronger the spin, the slower the clock. Einstein's equations tell us that this isn't magic. It is gravitational time dilation. Time runs more slowly in regions of stronger gravity or faster motion. When you are close to a massive spinning body, space-time itself is pulled into its rotation. You cannot stay still. You are dragged along as if the universe itself is rotating you. This phenomenon is especially extreme near Kerr black holes that spin. Named after the mathematician Roy Kerr, who first solved Einstein's equations for a rotating black hole in the year 1963, a Kerr black hole is perhaps the most exotic structure we know. Unlike a simple non-rotating black hole, which merely pulls everything inward, a Kerr black hole spins spacetime around its axis. Close enough to the event horizon, the speed of that rotation approaches the speed of light. Nothing, not even time, can resist being dragged along. The region outside the event horizon where this frame dragging occurs is called the ergosphere. Within it, nothing can remain stationary relative to distant space. Every particle, every photon must rotate with the black hole. It is as if space itself becomes liquid, spinning in a vast, invisible whirlpool. In the year 2021, using NASA's Chandra X-ray Observatory, scientists observed matter spiraling around a black hole at the center of galaxy M87, confirming that it rotates near the limit predicted by relativity. Inside that whirlpool, time behaves differently. If you could hover safely near the ergosphere, an impossible feat for now, your clock would tick slower than those on Earth. For every minute you experience, hours could pass for the rest of the universe. Einstein called this the warping of time, a direct consequence of motion and gravity acting together. As he once wrote, "Time and space are modes by which we think, not conditions in which we live." The European Space Agency's Event Horizon Telescope captured the first-ever image of a black hole's shadow in 2019, and later in 2022 released the image of Sagittarius A, the supermassive black hole at the center of our galaxy. The luminous ring we see is not light from the black hole itself, but from matter spiraling around it, light bent and delayed by space-time curvature. Those glowing arcs are visual proof that rotation and gravity together can bend not just light, but the flow of time. The same laws apply on smaller scales, too. Even satellites orbiting Earth experience tiny time differences. The Global Positioning System, GPS, must constantly correct for both gravitational and velocity-induced time dilation. If left unadjusted, GPS clocks would drift by 38 microseconds per day, enough to cause navigation errors of several miles. So, even here, where space-time seems calm, the bending of time is not theory. It is part of daily life. When astrophysicists simulate the regions near a Kerr black hole, the mathematics becomes breathtaking. Rotation can twist spacetime so sharply that closed time-like curves appear, paths where a particle could, in theory, loop back to an earlier point in time. Whether these loops are physically real remains uncertain, but they emerge naturally from Einstein's equations. In these extreme environments, past and future lose their fixed meaning. The James Webb Space Telescope, with its infrared precision, now observes the accretion disks of distant quasars, galaxies powered by supermassive rotating black holes. JWST's spectra show light from these disks stretched and redshifted, a sign that time runs slower in those regions. some of the light we detect today left those spinning giants over 13 billion years ago, meaning we are watching time itself stretched across the cosmos. Rotation, it turns out, does not just shape matter. It defines how time flows near it. The faster and denser the spin, the greater the warping of spacetime. From our gentle planet to the violent hearts of galaxies, the universe uses spin to sculpt both motion and time. What we call now is different everywhere, depending on how fast and how deep the local spacetime is turning. Even light, which normally travels at the universe's ultimate speed limit, is forced to bend and slow near rotating masses. NASA's NuSTAR and XMM Newton missions have captured X-ray echoes around black holes. Light trapped briefly in rotation before escaping. In these echoes, time stretches like a soft thread. Measurable, predictable, yet endlessly strange. One might wonder, then, whether the universe itself is twisting time on a grand scale. Large-scale cosmic rotation could subtly influence the way time flows across billions of light-years. While current cosmological data from the Planck satellite show no strong evidence for universal spin, the question remains open. Even the faintest twist over cosmic distances might leave fingerprints in the polarization of ancient light, hints that time itself has a preferred direction. As physicist Kip Thorne, co-author of The Science of Interstellar, explained, in the warped spacetime near a spinning black hole, the future of one observer can become the past of another. Rotation does not just bend trajectories. It bends the sequence of events, the very rhythm of existence. And yet, for all its strangeness, the effect is consistent and measurable. Time dilation around rotating bodies has been verified by atomic clocks aboard aircraft, satellites, and in mountain laboratories. The faster you move, or the deeper you fall into gravity, the slower your time flows. It is not an illusion, it is the universe keeping perfect balance. So, yes, rotation can bend time, but what is even more intriguing is why that bending seems to follow a pattern, a smooth, universal law that links motion, gravity, and energy into one continuum. From Einstein's equations to every ticking satellite, it all points to one truth. The universe does not just move through time, it creates it through motion. Take a slow breath. Right now, your own sense of time is tied to Earth's gentle spin, the sun's pull, the galaxy's turn. You are surrounded by motion so precise it writes the seconds you live in. And if rotation can bend time, what happens when time starts to control the spin? That is the mystery waiting in our next chapter. Part 5. If spin controls time, who controls the spin? Every second you live is shaped by motion. The ticking of your watch, the pulse of an atomic clock, even the rhythm of your heartbeat all depend on something spinning. Electrons rotate inside atoms. The Earth turns once every 24 hours, and as it spins, it drags spacetime just enough to change how time flows. At the equator, where Earth's surface moves fastest, about 1,037 miles per hour, clocks run slightly slower than those at the poles. It is not because of temperature or air pressure, it is because of relativity. Einstein's theory showed that motion and gravity can stretch or compress time depending on how fast and how deep you are in a gravitational field. So, yes, spin controls time, but the question remains: who or what controls spin? To answer that, scientists look at the most reliable keepers of time humanity has ever built: atomic clocks. Inside them, electrons whirl around atomic nuclei at fixed energy levels. When they jump between those levels, they release photons at an exact frequency. That frequency, defined by the cesium-133 atom, sets the length of 1 second, 9,192,631,770 cycles of radiation, corresponding to the transition between two hyperfine levels of the ground state of the cesium-133 atom. Those words, printed by the International Bureau of Weights and Measures, describe how every second of your life is calibrated to a tiny atomic spin. The rotation of electrons inside atoms is a kind of quantum spin, not a physical twirling, but a fundamental property of matter. In quantum mechanics, particles carry spin values that determine how they behave in magnetic fields, how they bond, and even how they obey the Pauli exclusion principle, the rule that no two electrons can occupy the same quantum state. So, at its smallest scale, timekeeping depends on spin, not the turning of a planet, but the internal angular momentum of atoms themselves. But just as atomic spins govern time inside our laboratories, planetary spins govern time on a cosmic level. The Earth's rotation defines the length of a day, while its orbit around the Sun defines the length of a year. These motions aren't fixed, they slowly drift. Tidal forces from the Moon are gradually slowing Earth's spin, adding 1.7 milliseconds per century to each day. To keep atomic time and planetary time synchronized, scientists use a system called leap seconds. Occasionally, the world's atomic clocks are adjusted by 1 second to align with the planet's natural rotation. In a sense, we are constantly recalibrating human time to match Earth's cosmic spin. If you compare clocks at different latitudes, the differences are measurable. A clock placed at sea level near the equator, moving fastest due to Earth's spin, runs slightly slower than one placed high in the mountains or near the poles. This is both special and general relativity at work. As NASA explains, a clock on the equator ticks more slowly than one at the poles because it is moving faster and is deeper in Earth's gravitational potential. The difference is tiny, a few nanoseconds per day, but real. Your phone's GPS system must correct for this effect constantly. Each of the 24 GPS satellites orbits Earth at about 8,700 miles per hour, 12,500 miles above the surface. In orbit, they experience weaker gravity and higher speed, causing their onboard atomic clocks to run faster by about 38 microseconds per day. If uncorrected, this would make navigation errors of several miles accumulate every few hours. To keep time consistent, engineers combine Einstein's equations with real-world measurements, literally adjusting for the curvature of spacetime caused by Earth's rotation. So every time you check a map or receive a location signal, you are witnessing relativity in action, a quiet collaboration between gravity, motion, and spin. But who started the spin in the first place? Astronomers trace it back to angular momentum, a conserved quantity in physics. When the solar system formed 4.6 billion years ago, a cloud of gas and dust collapsed under gravity. As it shrank, it spun faster, just like a skater pulling in her arms. That primordial motion distributed angular momentum to everything inside: the Sun, the planets, their moons. Each body still carries a portion of that ancient rotation. No external force continually keeps them spinning. They continue because of inertia, the same law that keeps a planet in motion until something resists it. In space, where friction is nearly absent, spins can last for billions of years. So the answer to who controls spin is no one. Once set in motion, the universe needs no hand to keep turning. But the relationship between spin and time grows stranger the deeper we look. Inside atoms, spin determines energy states. On planetary scales, spin defines days. On cosmic scales, spin drags time itself, and all these levels are connected by one law: angular momentum is conserved. Time, in that sense, is not an independent entity. It is a reflection of how energy and spin interact. In the year 2016, the European Space Agency's Gaia mission mapped the precise motions of over 1 billion stars in the Milky Way. The data revealed that our entire galaxy rotates once every 230 million years, carrying the Sun and its planets along in a vast spiral. Each star's orbit contributes to a grand cosmic timepiece, one rotation marking the rhythm of galactic time. Just as atomic spin defines seconds, stellar spin defines aeons. Even the Sun spins once every 27 days at its equator, but not uniformly. Its poles rotate slower, a phenomenon called differential rotation. This twisting motion generates magnetic fields that shape solar flares and coronal mass ejections. When those magnetic storms reach Earth, they distort our own magnetic field and can even affect satellites and power grids. So, from the atomic scale to the solar scale, spin is not passive. It sculpts fields, defines rhythms, and interacts with the very tools we use to measure time. Einstein's relativity linked these patterns beautifully. In his equations, the geometry of spacetime depends on energy and momentum, including angular momentum. In other words, spin curves time. If you remove spin, spacetime becomes simpler, flatter, less dynamic. Add spin, and it warps. Gently for planets, violently for black holes. We might then say that time itself is recorded in motion. The second is written in atomic spin, the day in planetary spin, the cosmic epoch in galactic spin. Everything that moves measures, and everything that measures moves. In the year 2022, the James Webb Space Telescope observed distant galaxies whose light has traveled over 13 billion years. Even in those primordial galaxies, astronomers detected rotation, a sign that angular momentum existed almost immediately after the Big Bang. That means the law connecting spin and time has been in operation since the universe's earliest seconds. Spin is not a product of time. It is part of what gives time its flow. So if spin governs time and spin itself arises naturally from the conservation of motion, then who or what controls it? The most precise answer science can offer is, the universe controls itself. Every spin is balanced by another. Every slowing motion is matched by an exchange of momentum elsewhere. Even the smallest quantum particle obeys these same equations, ensuring that angular momentum remains perfectly conserved across space and time. NASA's Jet Propulsion Laboratory put it simply, the laws of motion do not change. The universe runs on balance. What is lost in one place is gained in another. There is no master, clock, no hidden hand. The very act of motion maintains its own timing. Spin, then, is the universe's internal gyroscope, its built-in way of keeping everything aligned. From your atoms to the stars above, the same principle governs every scale. Even when systems decay, collide, or slow down, their angular momentum transfers onward, keeping the cosmic clock ticking. And so, when you ask who controls the spin, the universe gently answers, no one must. Motion is self-sustaining. It is the quiet balance that underlies both time and existence. Take a breath. The atoms within you spin in harmony with the turning Earth, the orbiting moon, the spiraling galaxy. You are already part of that motion. Every heartbeat is a fraction of a universal rhythm that began long before clocks, calendars, or light itself. And as that rhythm continues, another question slowly rises. One that stretches beyond motion into the structure of the cosmos itself. If the universe depends on perfect balance, what happens when that symmetry breaks? That is where we drift next.